In all the sections we are doing this year, this is way down on the importance scale. It just isn't used very often. The good news is that it's a quick and easy section to go over. Well, it's quick and easy if you remember the properties from the last section, that is. In section 6.4 we had this theorem, which said that if we had a rhombus, then we knew the diagonals were perpendicular. Well, the converse of this also works. Instead of starting with a rhombus and then knowing the diagonals are perpendicular, the converse starts with the diagonals perpendicular, and that is enough to show that a parallelogram is a rhombus. It doesn't come up very often, but if you wanted to use it in a proof, you need to either write it all out or abbreviate it since it has no official name. I would suggest something like this. Probably not too surprising. If you think about it a second, you can even probably guess what comes next. Last section we had this theorem that said that the diagonals of a rhombus bisects the opposite angles. Like before, the converse also works, although there is one little tweak. This converse basically does the opposite, but I highlighted the one change. Rather than needing to show that both diagonals bisect a pair of opposite angles, all you need to do is show that one of the diagonals bisect a pair of opposite angles. So that cuts down your work. You only need to do one diagonal, not both. It doesn't have an official name, so you need to abbreviate it as a reason in a proof. Other than that, it's pretty straightforward. Just flip the two special properties from last section around, and you can use them to prove a parallelogram is a rhombus. We also did one special property of a rectangle last time. This is that theorem. Rectangle diagonals are congruent. And guess what comes next? We flip it around. If you can show that a parallelogram's diagonals are congruent, that will let you prove a parallelogram is a rectangle. Once again, no official name, so you'll need to abbreviate it if you want to use it as a reason in a proof. You might do that all of twice this year. That's all there is to this section. There are actually 3 ways to prove a parallelogram is a rhombus. We did 2 this section, but you can also use the definition to show that a parallelogram is equilateral. Any of those 3 things will allow you to prove a parallelogram is a rhombus. Similarly, there are 2 ways to prove a parallelogram is a rectangle. There is the one we just covered, but you can also use the definition of a rectangle and show that the parallelogram has 4 right angles. Either one works. We haven't talked about squares yet, even though they are in the title of this section, but there isn't a special way to prove a parallelogram is a square. It's just a 2-step process. Show that the parallelogram is both a rhombus and a rectangle. Show one of the 3 things at the top to show it is a rhombus, then show one of the 2 ways that you can show it's also a rectangle. That's all you do.